The next topic, and essentially final topic in the course, concerns general impedance matching, albeit where we're only concerning ourselves with a single frequency operation. So the scenario really is that we could imagine having some load impedance ZL, which in general have a real part and imaginary part. And typically it will be connected to a generator via a lossless transmission line, in our approximation at least, whose characteristic impedance is Z0. Of course, associated with the line will also have a phase coefficient beta, which is twice pi over lambda. And for air core lines, to reiterate, lambda is the speed of light divided by the frequency of operation. Now, in general then, the generator will launch a wave, or waves propagating from the generator will propagate along the transmission line, and when they impact upon the load, we will get a certain proportion of that incident voltage wave reflected with a decrease in its amplitude and also an associated phase shift. Now, in general, reflections are not desirable because, first of all, we won't be getting maximum power transfer from the generator to the load. And secondly, we can get, in the case of where we have more complex waveforms, say, for example, square waves or digital data and so on, we get the multiple reflections on the line. And how those multiple reflections then are absorbed by the load will give rise to a distortion essentially in the signal, composite signal across the load, which is certainly not, of course, desirable. So our whole goal here is to somehow try and avoid reflections going back to the generator. So essentially, again, to reiterate, if ZL is not equal to Z0, a wave will be reflected from the load back to the generator. And to avoid such a reflected wave reaching the generator, the load must be what's called impedance matched. So to obtain the impedance match condition, we need to insert somehow in the main transmission line a matching network. Now, the matching networks we're going to look at will simply consist of transmission line lengths and also transmission lines perhaps in parallel, that is in shunt to the main transmission line. We're only going to look at one particular type of matching network, which is called a single stub matching network. Now, if the load has a resistive component, then maximum power transfer will also occur, which means we get maximum power transferred from the generator, eventually, of course, into the load resistive component. So we have to design this matching network in such a way that its input impedance, we'll call it ZIN, is actually equal to Z0. So as far as the generator is concerned, looking inwards here to its right, into the input of the transmission line, it too will see an input impedance equal to Z0. And we know if such an input impedance is equal to Z0, then we get no reflected wave back reaching the generator. That's not to say there won't be any waves bouncing up and down here between the matching network and the load impedance. So in the impedance match condition, at the interface between the matching network and the transmission line facing the generator, the input reflection coefficient will be equal to 0, and thereby no reflections will occur back towards the generator. We're going to assume that all our transmission lines are air core lines. We'll call the generator frequency F. Of course, in particular examples, problems, we'll actually put an actual numerical value on F. It has an associated angular frequency omega, and the wavelength then of the electromagnetic wave in the transmission line material, lambda is equal to c divided by f, c being the speed of light in free space. Now, we'll be dealing with impedance matching networks which involve transmission lines quite often are usually in parallel with the main transmission line here. And in dealing with parallel type circuit elements, transmission lines and so on, we're much better off dealing in terms of admittance. So admittance is basically in parallel add, which is easier than combining impedances in parallel. So if we look at the load impedance here, ZL, it has an associated admittance, which is simply the inverse of ZL. And then we'll also define in a similar fashion, the characteristic admittance of the line is simply the inverse of the line's characteristic impedance. Now, in terms of impedance matching, I've already mentioned that we have to design an impedance matching network such that its input impedance Zin is equal to Z0, which of course is the same as saying that its input normalized impedance is equal to 1, which in terms of admittance then means that we want an input admittance equal to Y0, which in terms of a normalized input admittance, we'd like it to be equal to 1. A normalized admittance, of course, is simply admittance divided by Y0. That's all that is. So we're going to work in general in terms of admittance, but quite often then we need to revert back to getting impedance in some problems. Now again, back to our scenario that we had in the previous slide. Here is our definition of normalized load impedance, which is simply the load impedance divided by Z0. The load admittance is the inverse of the load impedance. And the normalized load admittance is simply the load admittance divided by Y0, which of course is the same as YL multiplied by Z0. And again, for impedance matching to occur, we require that the matching network normalized input impedance Zin is equal to 1. Therefore, we require that the normalized input admittance is also equal to 1. Because of course, the normalized input admittance is simply the inverse of the normalized input impedance. So both of them are going to be equal to 1. Now this year, we're only going to consider single stub matching network design. So in previous years, I've also considered double stub matching network design, but it's not easy to both explain double stub matching network design using PowerPoint presentations, but also certainly not easy to do actual problems. So I'm going to omit that topic this year. Because our impedance matching networks will essentially be shunt type networks, we're going to use a Smith chart principally for admittance calculations, which makes the design of impedance matching networks much easier than would be the case if we work directly in terms of impedance. So of course now I have to explain how we can use a Smith chart for admittance calculations. So back first of all to some general concepts which we met before. Recall that an admittance Y in general can be expressed as having a real part G and an imaginary part B. So it's essentially a shunt that is parallel representation of a circuit. So G, of course, here, capital G, is the conductance, and B is called the susceptance. So here's the shunt representation. If we had some circuit element modeled, for example, by an admittance Y, of course the inverse of Y is simply its impedance Z, then Y here, its equivalent circuit in terms of real and imaginary parts, is really essentially a resistor having conductance G. Of course, the inverse of G will be the associated effective resistance. And that G value is only equal to the inverse of the real part, that is R, of Z, only if X is equal to 0. That is the reactance associated with Z. And so here's a parallel element JB, basically. Now recall, of course, just to refresh yourselves, an inductor L has admittance 1 over J omega L, which of course is minus J over omega L. So it has negative susceptance. Its B value is negative, which is minus 1 over omega L. The inductive susceptance is 1 over omega L, which is a positive quantity, but the actual susceptance, of course, is a negative of that. A capacitor C will have admittance J omega C, so it actually has positive susceptance omega C, which is often called then the capacitive susceptance. So you need to be clear there. The susceptance of an inductor is negative. The susceptance of a capacitor is positive. But what's called inductive susceptance is typically written down as a positive value. Now, following off of this then, in terms of normalized admittance, which is simply y divided by y naught, which of course is simply capital G plus j capital B divided by y naught, we can write that as equal to little g plus j little b. So little g is called normalized conductance for obvious reasons, and in a similar sense, little b is called normalized susceptance. So we've got little g and little b. If little b is positive, that's a capacitive type susceptance. If little b is negative, it's an inductive type susceptance. Next, I want to explain how the Smith chart can be used for admittance and related calculations. Now again, to recap, the Smith chart is located essentially in the reflection coefficient plane, but limited to the unit circle. So along here we have the real axis essentially, real part of the reflection coefficient, and directly upwards and downwards in the center point we have the imaginary axis, i.e. the imaginary component of the reflection coefficient. Now it turns out that in the reflection coefficient plane, the equations for G and B in terms of the real and imaginary parts of the associated reflection coefficient are actually identical in shape to those of the R and X circles. So identical in shape. Now of course, R and X circles have got to do with impedance, and G and B circles have got to do with admittance. So if we look first of all at the G circles in the Smith chart, now they're actually marked in the Smith chart along the real axis here, and marked as such in terms of the conductance component G divided by y naught, which of course is normalized conductance. So along here. So for example, if we were concerned with a G equals 0.3 circle, there it is. A G equal to 1 circle is over here, going right through the center in fact, and ending on this 1, 0 point over here. Now in fact all of those G circles all share a common point over here, which is the 1, 0 point. And we notice here as G gets bigger and bigger, the circles reduce in radii. The radius gets smaller and smaller. So you can see there's the G equal to 50 circle. So this 1, 0 point over here has a G value equal to infinity. So next we move on to looking at the B circles. So in the upper half of the plane, the B circles are positive. And because, of course, a B value which is positive is essentially a capacitive susceptance. And it's labeled on the chart as capacitive susceptance JB divided by Y naught. So all these B values are along here. And when B is equal to 0, they associate a circle as infinite radius, and thereby it corresponds to the real axis for that B circle value. B equal to 0 is the real axis. And as B gets smaller, bigger and bigger rather, larger and larger, the circles decrease in radius. You can see here. And of course, we're only concerned with circles within the unit circle. Then those circles end up at this point here, the 1, 0 point, where basically little b is equal to infinity. So that point over here, the 1, 0 point on the chart, in terms of normalized admittance, the point has a G value equal to infinity and a B value equal to infinity. And of course, because the inverse of admittance is impedance, the inverse of basically infinity is 0. So that point over here, in terms of admittance, represents an ideal short circuit, which we'll come to later on again. Now back down to the lower half then in terms of the B values, or B circles. Those B circles are identical in shape to the upper B circles, but reflected effectively through the real axis, just like we had for X circles. So in the lower half of the chart, the B values are intrinsically negative, although marked positive. So those values of B, positive values, are associated with an inductive susceptance, and on the chart are labelled as such as being inductive susceptance minus J capital B divided by Y naught. So when we're using those actual values in real calculations, numerical calculations, we make sure that we convert them to negative values. So back to the particular points. That point over there, 1, 0, represents, if we're dealing with admittance on the chart, it represents an ideal short circuit. And this point over here, minus 1, 0, would represent an ideal open circuit. Because at that point over there, basically G is equal to 0 and B is equal to 0. So the inverse of an admittance having a G value equal to 0 and a B value equal to 0 is impedance, and of course inverse of 0 is infinity, which is an open circuit. So 0.10 represents a short circuit when we're dealing with admittance points only, and 0.10 represents an open circuit again when we're dealing with admittance points only. If we're dealing with impedance, then the reverse situation would apply. Now some more points. If we happen to plot a normalized impedance point, P we'll call it, on the chart, so of course having an R value and an X value, then the inverse of that point, I'll just call it Q for example, the inverse of that point of course is normalized admittance. And if we wanted to find that graphically, we could simply do that by reflecting the point P an equal distance through the center of the chart and then reading what we would now call the closest G and B circles at the point Q to determine the associated normalized admittance. So reflection of an impedance point through the center essentially converts it to an admittance point, and the associated circles then at that admittance point are interpreted to be G and B circles. Of course, we can do the opposite thing as well. If we have an admittance point, to get the associated normalized impedance, reflect it through the center of the chart, and then interpret that point then as being an impedance point whose value can be obtained by the closest R circle and X circles to that point. If Q happens to be a normalized admittance point, for example, in general, then the magnitude of the reflection coefficient is carried out. To find it, we do it in exactly the same way we do for an impedance point. Is simply the length of the line from the center of the chart to the point itself. And to obtain the reflection coefficient angle, we do this by drawing a line from the point Q, normalized admittance point, through the center of the chart and continuing on to the opposite side of the chart until it intersects the voltage reflection coefficient scale, and then we read the associated angle. So that's quite simple as well. And a very important note here is that the input impedance and the admittance of a lossless transmission line, which is terminated in a short circuit or open circuit load, will only have an imaginary part. And the value of that imaginary part will depend on the length of the line in terms of the number of wavelengths or fraction of wavelengths. Because of course, a lossless line can't dissipate any power, energy, and a short circuit can't dissipate any power or energy, and an open circuit can't dissipate any power or energy. So that means looking inwards will, into such a transmission line terminating in a short circuit, open circuit, we can have no real part to the input impedance or the admittance, because there's nothing to dissipate energy.